the title is on non-positively curved cubing of alternating nodes. Please.
Thank you very much. Today I'd like to talk about this theorem, and I'd like to give some application to this theorem. This is joint work with Makoto Sakuma at Hiroshima University. And yesterday I was informed from Stavros that Stavros already has another approach to this theorem, which I explain from now. And anyway, our approach is very surprisingly simple. Anyway, let me explain our approach first. So the statement is following: if K is alternating, the S, what is this? S is the ideal triangulation of alternating knot complements, which is used in the study of Polygon conjecture. That is, each tetrahedron corresponds to explanation around there. In triangulation, whose tetrahedron here? Q factorial to Q in Kashaev. So the essentiality of each edge in such decomposition is very important property. And this time I can prove the for alternating complement. Okay, and the exterior is not only K, but also the interior of regular neighborhood of K. It is called exterior. So an edge in a properly embedded edge in exterior is essential. It cannot, if we cannot push in the boundary bimonodally. That's okay. Thank you. And I don't explain the detail of this decomposition, but I just show you all the edges in S in the next slide. This one. Can you see it? So there is 4 colors, I think. Red one here, and blue one here, and a gray one. It's very short, so I'm afraid you can see this, and green one. But it is a little bit complicated. So I classify these edges into 4 types: type A and type B and type C and type D. So from next slide. First, we begin with type A. This one. This type, one end of this type edge is one end is each overcrossing point, something like this, and the other end is common, this overcrossing point, and goes to around North Pole and go back to this overcrossing. So we have some number of this one, and this one, and this one also, and so on. So this is type A. So if we have n crossing, we have n-1 edges of this type. So next is A comes from above, maybe. So next is type B. B comes from below. So it's a proper name, I think. So one end is each undercrossing, something like this, and one end is common. At this common undercrossing points. So for convenience, I shall call this crossing entrance and this crossing exit. Oh, please remember. So this is type B. So the number of type B edges is same as the number of type A edges. And next, is there any problem? Okay. The type C. C comes from crossing. So you can find very small, short gray edges at each crossing. But it is already well known that this type of edges are essential in the complement because it is very famous surface for alternating knots, so-called checkerboard surface. So you draw the white and black, something like this. Then such checkerboard surface is known to be incompressible in the complements. And this gray edge is lie in such incompressible surface, so they are automatically incompressible. So in this talk, we skip this gray type, type C, completely. So this is final type, a little bit complicated. It corresponds to each face or in each domain of the diagram. So this D comes from domain. So it goes like this. At one end is overcrossing at the entrance, and the other end is undercrossing and exit. But in the intermediate step, it penetrates from north pole to south pole. It penetrates this, for example, this edge, it penetrates this domain region. So we have some number of regions in general. So this type exists correspond to each faces of diagram. But please remember that for this region and this region, to this couple of regions is adjacent to the entrance. This one, for example, this edge. So we go up to North Pole and penetrate this small region, and they end up with this point. But at this point and this point is connected. So this is moved to this one. So this edge is something like this. It's this kind. So it's homotopic to blue one. Some type B edges. I think this one. Can you imagine? Perhaps I think it is homotopic to this edge, this one. And so I color it blue. So what I want to remember is that the couple of regions which is adjacent to the entrance can be ignored. So this type, the edges of this type correspond to the regions of diagram except these faces, and similarly these edges. So corresponding to these domains, the edges corresponding to these domains are isotopic to some red one. So we ignore this couple of edges. Okay. So summarize. This type of edges exists corresponding to the faces except this one and this one and this one and this one. That's it. Then section 2. So this is main object in this talk, and I learned from Adams' paper, which is taught by Sakuma. And Adams, in his paper, he also says that he was suggested by Ego, but Ego, I don't know Ego knows this decomposition, but anyway, Adams says so. So perhaps due to Adams or Ego. So this is ideal triangulation using the volume study in volume conjecture, which explained by Otsuki yesterday. So he suggests that. So initially we have 4 triangles around this edge of type C. This one, this one, this one, and the backside one. To this a couple of cubes and truncate this one. So we have initially we have ideal vertex, but truncate by S. So it's now boundary of the exterior X. So I denote exterior by X. This is a good name, I think. And this is no longer ideal. This point and this point goes to North Pole, and this blue point and this blue point goes to South Pole. So never ideal at all. And we divide this truncated octahedron by horizontal green plane like this. So such green faces is gathered. It is well known Dane complex, I think. Okay, so by switching in this manner, we can easily decompose X into a collection of cubes. This is calling Adams polygon. And we first identify each cube with a unit cube in Euclidean space, 3-dimensional Euclidean space. We can regard X as a piecewise Euclidean complex. So there is nice theory about such metric space, which I explain in the next slide. Anyway, such X is called cubed complex in this talk. Okay, so we study prepare some elementary facts such metric space. So perhaps if you are interested in this subject, I recommend the book by Riderson Hefliger. The title of their talk book was metric spaces of non-positive capture, something like that. A nice book, but very thick. I just learned from that book. Very elementary. That's so. first metrize this space. So it goes like this. A path in X is called piecewise geodesic. If decomposes into some pieces, this one, and each piece belongs to some cube. So this is a simple definition of piecewise geodesic. And then by elementary argument, there always exists a shortest piecewise geodesic between 2 points. So we call such line, such curve geodesic, and then X becomes a geodesic metric space. Very easy. And this is definition. So please remember this notation: length of X at X. So X is some point in X, and we gather unit tangent vectors at X. Then it's just denoted. So it calls geometric length of X in X. So it is some epsilon neighborhood around X almost, which I explained by picture from in the next slide. Okay. Then the following lemma is well known. A piecewise geodesic, local geodesic, if for each point of X. So if we look at the length of X around in X, then a distance between length X of X is topologically a sphere. That sphere is decomposed into spherical triangles. So such space is metrized in this manner also. So we can consider this is also another metric space. And then, so by using such metric, distance is measured between incoming and outgoing vectors at least pi. Then such curve is local geodesic. This is a well-known lemma. Not so difficult to prove. So geodesic part is over. So now a curvature I explain. Metric space. This is very famous definition due to Gromov. Metric space is said to be non-positively curved or locally capped zero if each point of each point of X has some small neighborhood where any geodesic triangle, something like this. This is the geodesic triangle in X. Any triangle in a small neighborhood of point, we prepare a comparison triangle in Euclidean, two-dimensional Euclidean space. The length of this edge is same as this one is, and the length of this edge is same as the length of this arc segment, and the length of this geodesic is same as the length of this one. So we prepare this comparison triangle here, and we choose any 2 points on the geometric triangle in X. This one and this one, say X and Y. So this distance by X and Y, we have corresponding points X dash and Y dash here, and this distance is less than this one. If such condition is satisfied, we call such condition very roughly, right? But if this condition is satisfied, such metric space is called non-positively curved. Very, very famous notion, I think. So there is a very combinatorial way to check such non-positively curvedness. There is good condition, so-called Gromov's ring condition. A cube complex is non-positively curved if length of X is simplicial complex. So simplicial is very important because this simplicity breaks in a non-alternating knot case. If K is alternating, our X is simplicial complex. And further condition here, any finite subset of vertices that is fairly joined by edges spans the simplex, any dimension. So for example, you have triangle here, then it should have span 2 cells. And if you have K4, you should have it should span 3 cells here. So that condition. That's a Gromov's ring condition. Then proposition goes like this due to Adams, but he never writes his proof, so I shall explain briefly. from the next in the next slide. The exterior X of the alternate node, and it's double across boundary of X. I shall explain. X and prepare its minus X and glue them along the boundary of X. Then we have a closed line. I shall denote this W. So and call W. Okay. So this is non-positive. First, we can check. At the same time, we can check that this condition for X and W. But if we check the condition, this condition for X, then perhaps the checking for check for W is automatically, I think. Okay. So it's a brief. Here is a brief proof. So we look at a link around each vertex. So the north pole is a typical one. So it's denoted by plus infinity. And it's something like equal to neighbor, so it becomes this sphere. And another one is north and south pole, neighborhood of south pole, boundary of the neighborhood of south pole. This one. So this one and this one is I detail describe in the next next slide. And what we're discussing is this one, hemisphere. So we have one vertex on the boundary of X. So please consider the regular neighborhood of this node is my R. Then you have vertex here. So its link around that vertex is something like this. It's a hemisphere. This hemisphere is that. So this is similar one. So we look at this and this simultaneously. Then we use here the alternativity. So this is overcrossing. The next one is undercrossing. So I'm sorry. No. I omitted the overpass. This is another crossing, and here should be another overcrossing, but I omitted. It's not. This is overcrossing, and this is undercrossing. Also, this is undercrossing. So this hemisphere comes from made up with this triangle. It's a neighborhood of this point, and this point goes to this point, and this triangle. And another two, it comes from this. Can you see? And this very, very thin. But this vertex and this vertex gather here, and also this vertex goes to the same point. So then this four triangle gathers and makes this hemisphere. So the Columbus ring condition is clear. And the lower hemisphere is similar situation, and I shall omit. Okay. So remaining this, a little bit go back. I described this one. So description of this one is very similar to this one. So I shall omit this, and I describe this sphere. But sphere is hard to draw. So we develop this sphere plane in the next slide. Yeah. So here is the introduction. So we draw diagram, original diagram here, and erase after. And we first prepare the diagram of the diagram. We consider four regular graph as a diagram. So green one is the diagram. And please note that this is bipartite, or in other words, this only contains, never contains autocycles. So in particular, never contains triangle. Please remember. And then each face of this green graph, we have in the center of this face, not just exactly center, but anyway, in the center we have original crossing. Not crossing here. So we take star subdivision from this vertex, something like this. You can see. So this is original face, green face, and here is the center, and take subdivisions, start subdivisions like this, and ignore the original, not that. So this is nothing but the link, geometric link of the North Pole. The South Pole is similar. Okay, so this is easy to observe that. It is easy to observe that the red edge, newly added subgraph, is also bipartite and never contains autocycles. So we are going to check the ground string condition of this for this diagram, this graph. But if we have triangle, then there is no green triangle and there is no red triangles. If we have triangle, it contains red one at least one and green one at least one. But if such triangle contains some red edge, then red edge should be followed by another red edge. So such triangle consists of two red edges and one green one. Such triangle is this one. So it corresponds to each edge of original octagon. So it spans two symmetrics. And so my explanation may not be good, but it is very easy to check the ground string condition for such graph. Anyway, this completes the proof for the non-positive curvedness of alternate knot complements. Okay, now we go to the proof of theorem. Is it too fast? My eye position is lower than the slide, previous slide. So this is geometric ring of the North Pole, and this is the geometric ring of South Pole. And please I shall remind you the edge of type A. Let me go back. The edge of type A is this one. So this edge can be realized by this one. Start from this point, overcrossing at the entrance, goes to North Pole. This is so here in North Pole, and go back through this point to this overcrossing. So this one and this one is one edge of type A. And we check the local geodesic condition. So the star of this complex, star means ordinary meaning of complex, a simplicial complex. The star is dark gray, colored by dark gray, like this. And the star of this vertex is colored by dark gray here, like this. And this star and this star is, in particular, interior is never intersect. But if we go out from this vertex to the boundary, we have to move at least pi over 2, because this is, this triangle is nothing but each triangle comes from this. This is a spherical triangle. So we suppose the unit tangent vector. So this, please consider the radius is 1. So the length of this r is pi over 2. So each triangle is spherical triangle is congruent to this spherical triangle. So we have to move at least pi over 2 from this vertex to the boundary. Similarly, we have to move pi over 2 from this vertex to the boundary. So the distance of this vertex and this vertex at least pi. So this satisfies the local geodesic condition. So this edge is local geodesic in X. Okay. So similarly, the edge of type B is realized by something like this. So it's also local geodesic in X. And finally, I skip the edges of type C, and finally we go to the edges type D. It is a little bit complicated. So we start from here, and go to this point, and go to North Pole. And then through this point, we penetrate this region. And through this point, we go to my South Pole. And through this point, we go up, end up with this undercrossing at the exit. So this edge has two vertices here and here, and we check the local geodesic condition. It's very similar. The star of this vertex is colored like this. The star of this vertex is like this. Their interior never intersects, and so distance of this vertex and this vertex is less than or equal to pi. This is similar. The only dangerous case is that this green vertex becomes this one and this one. Okay. Remember that? Do you remember? This vertex and this vertex correspond to. I go back to very first one. I'm sorry, this one. Correspond to this blue one and this blue one, which I put away already. So similarly, this one correspond to this vertex and this vertex. So if we choose this vertex, then distance between this vertex and this vertex is just pi over 2. So it's no longer local geodesic. But we put away such dangerous vertex at first. So for other for the vertex correspond to other regions, such curve is becomes a local geodesic in any length. So, and proof theorem is finished here. Double over an edge E. So we consider some edge E in S. Then this is boundary of X, and this is X, and this is minus X, and they are glued at their boundary. So this is whole picture represent W. So this is an edge E in S, and this is its copy here. And geometric link of this vertex is nothing but a sphere. Just a double hemisphere, and the Grover's condition is easily checked. So, this edge, the distance between this point and this point is also just pi. So this is also a local geodesic loop in this case. This becomes loop because we take double. No, this is a properly embedded arc, and we take double. We have a loop, closed loop in W, and which is local geodesic. And this is important. It is well known that this is local geodesic in a complete non-positive curved space. Negative space cannot be homotopy; it's a constant loop. So this is well known. But by using this lemma, this loop is essential in W, which implies that this original properly embedded arc is essential in X. If this E is not essential, then this loop also not essential in W. So this completes the proof. So we have proved this theory. I think very easy by using such cubed complex structure. I was surprised that how fast saying this idea, but very natural and have some possibility to many other applications. So I should explain some applications to volume conjecture. So perhaps this picture you saw yesterday in Otsuki's talk. So if K is a hyperbolic knot in S3, we take its diagram, one rectangle presentation like this, and level each edge by from x1 to x7 in this case, and boundary to the boundary edges we put 1. In yesterday's talk, Otsuki put 0 and infinity to these dotted edges, but I omit this. And potential function, which appears in the integral expression of Kashaev's invariance, is given like this, very combinatorial. Each diagonal function corresponds to each corners, which does not touch the dotted edges. So we ignore this corner and this corner and this corner and this corner. And similarly, this one, this one, this one, this one we ignore. The other, for example, this corner, where is it? Yeah, this one, perhaps this one. So this order is crossing order. So we begin with this one and this one. So for this corner, we have this. For this corner, we have this. So how to take the ratio is I want. Explanation I want. Then, this is my old story, maybe up to 2010. But in that case, I was always assuming that the existence of essential solutions. Essential solution means that a solution to this equation such that each modulus, as this numbers represents the modulus of the ideal triangulation, ideal tetrahedron in the triangulation. So these numbers never belong to 0, 1, infinity, singular values. The such solution I shall call essential. I shall call essential solution. And in my old story, I always supposing the existence of such, not such factory. But now, if we suppose case alternating, then our theorem guarantees that existence of such essential, not only essential, but also geometric solution exists. So we must have geometric solutions, which is denoted by Z1 up to Zn for corresponding to hyperbolic structure. Then we we add some correction term here to original B, which is denoted by B0, just epsilon 1 to epsilon n, where epsilon nu comes from this one. So because this original equation is we take exponential. So original, if we remove this exponential, this guy is an integral multiple of 2 by I. So epsilon nu denotes such integer. So by such correcting such by such integral term, this is a kind of branch of B. So by making some correction, this B0 gives complex volume as a critical point. Note that Chern-Simons invariant for cusp manifold is defined modulo 1/2. So we have 2 pi square. Then it defined modulo pi square. So this puts here from that reason. And the Hessian of B0 at this point does not vanish. This is related to the non-singularity of the deformation character variety. Okay. So,
excuse me?
Why
does this Hessian does not vanish?
Pardon?
Why does the Hessian does not vanish?
Because at this point, due to perhaps Neumann-Zaki, the deformation variety is non-singular, zero. And I think it's already
The map to the deformation variety is not 1-to-1.
1-to-1.
The map from the deformation to the character variety is not 1.
2-to-1.
No, you have.
But I don't remember correctly, but in the paper, there is bijection between the deformation parameter u, a neighborhood of 0 to the character variety. So we have to talk.
That's all Neumann's part.
Oh, really?
I just calculate numbers.
Okay, I check again. That's you are negative to this session. Okay, I check again. Absolutely. So this is postponed. But anyway, when applying certain point method, this condition should be needed. And yeah, this is very contributing, and I should check seriously. And this is additional topic, invariant trace field. Okay, this is already observed by Cho with under the assumption that the existence of essential solution. But now, for alternate nodes, we are guaranteed we have such geometric solution, Z1 to Gn. So, invariant trace field is defined in this way. This is formal definition. So, the field generated by trace square of trace of each gamma. Gamma belongs to large gamma, but the large gamma is a holonomy representation of pi 1 into PSF2C. So this field is generated by our geometric solution. And further topic is here. So this is up to here. We are only considering the complete structure, but such complete hyperbolic structure can be deformed due to Sarson. And we consider the holonomies of meridian and longitude. So originally, at the complete point, the holonomy of meridian is up to conjugacy 1, 1, 0, 1, and longitude 1, something 0, 1. And it is eigenvalue is a little deformed. U. This U is usually used to parameterize such deformation space, and e to du, and longitude, eigenvalue of longitude go to e to b. Okay, and in Neumann-Zagier paper, b is observed an odd function of u. This is PQ density manifold is isomorphic to minus p minus q density manifold, I think. Yeah. So we can expand b like this in terms of u. So here's odd powers of u. And our corollary is this. We can explicitly write down each coefficient in terms of z1 to up to gn, a rational function of these guys. Perhaps recently I published on so g1 is famous. This is called cusp shape, and it is already known that it lies in this invariant trace field. But not only for C1, but also C3, C5, and in general C2n minus 1, we can express them by a rational function of Z1 to Gn. So, because we all belong to this one, so automatically this coefficient belong to also this K of Gn. So perhaps this is new. And this sequence it should be a little bit different from the sequence yesterday. So this is very hyperbolic geometric object, and there is another expansion. But it just happened. There's another actor it appeared here. Okay. Perhaps this is the end of my. Yeah, that's it.
Any questions or comments?
So, by doing this study, so if the value as a volume is positive, can you prove that the complement is hyperbolic?
No, it's difficult. At least we can construct a discrete phase representation from Z1 to Gn.
Yeah.
But to establish the hyperbolic structure, we exclude the negative or flat tetrahedron by hand. It's very hard. So
still exists negative tetrahedron.
yeah, yes. But in my experience, it's some typical type, I think. A kind of conjecture, so I never say yes.
Of course, alternating not have. If it's composite not, then maybe difficult.
Yes.
Prime not, then
Prime.
maybe you prove.
I think it is difficult.
Any questions or comments? Let's keep again.